Okay, so I will call this lecture 3 and 4. Okay, so we are in first section about this chapter, about the harmonically excited vibration, where there is a force applied on a mass as part of the system. Okay, and in this section, we will focus on undamped system, where the damping constant C equal to 0 or damping ratio equal to 0. So we can derive the response from the general equation we obtained last time from lecture 2, or we can derive this from scratch. So we have mx double dot plus kx equal to f naught cosine omega t. The system is subjected to a sinusoidal force given by f naught cosine omega t. The system is only a spring and mass, which is undamped. The solution will be two-part, homogeneous plus particular. Homogeneous is what we did. Okay, that is the homogeneous is C1 cosine omega nt plus C2 sine omega nt, and the particular is f naught over k minus m omega square cosine omega t. This is x. The particular is x cosine omega t minus phi, and x in general is given as f naught over square root of k minus m omega square or square plus c omega square. You put c equal to 0, you can reduce x to f naught over square root of k minus m omega square or square, so you can take it outside the square root because of the square here. Okay, so it becomes x equal to f naught over k minus m omega square, and the phase is tan inverse of c omega over k minus m omega square. But for c equal to 0, this will be tan of 0 equal to 0. Okay, and this is the total solution. The initial conditions are applied on the total solution. So we put at t equal to 0, x equal to x0 given initial displacement, and at t equal to 0, x dot equal to x0 dot again, which is given initial velocity. And then we can find C1 and C2. Okay, so we find x equal to x0 minus f naught over k minus m omega square cosine omega nt plus x0 dot over omega n sine omega nt, which is this is C1 and this is C2, plus f naught over k minus m omega square cosine omega t. So the response, the total response consists of two frequencies now, omega n and omega. This expression or this equation, the solution is the response for undamped system under harmonic excitation, but it will not be valid when omega equal to omega n, because we will have division by 0 here and division by 0 here. Okay, so this is valid for all omega except for omega equal to omega n. Not equal to omega n. Okay, so omega n is square root of k over m. So this is why when you substitute, when you take k as a common factor, you will have and here as well, you will have you take f naught over k, so this will be 1 divided by minus m over k, which is 1 over omega n. So this becomes 1 minus omega over omega n squared. The same thing here. So if omega equal to omega n, you will have division by 0. The particular solution, we study it more. We will plot the amplitude, x. Okay, this is x divided by f naught over k. So the amplitude ratio, that is x equal to f naught over k minus m omega squared. You can put this as amplitude ratio, which is xk over f naught will equal 1 over 1 minus omega over omega n squared. This is the amplitude of the particular solution. Although this is undamped system, but in practice there will be sort of damping that comes from either friction or internal bonding of molecules and air resistance. So it will the homogeneous solution will vanish after some time. So it might take longer than if viscous damping exists, but it will vanish at some time. So the focus on the particular solution. Okay, so I put the equation as amplitude ratio. So which is delta static is f naught over k. Okay, so here it is delta static is equal to f naught over k. Okay, this is the plot of the amplitude ratio versus the frequency ratio. In the equation, we have 1 over 1 minus omega over omega n squared. So if omega over omega n is less than 1, this quantity will be positive. And until we reach just before omega over omega n equal to 1, let's say 0.9 or 0.99. So we are approaching a division by 0. So the amplitude from frequency ratio equal to 0 to just before 1, the amplitude is increasing to plus infinity. Right, this is plus infinity. And when omega over omega n equal to 1, then we have a division by 0, which will go to infinity. Just after 1, when omega over omega n is, let's say, 1.1 or 1.01. So it is going to be, this quantity is going to be negative, and it's coming from minus infinity. So working in the region of resonance causes very large amplitude that comes from plus infinity to minus infinity, and then which put load on the spring that will break in very short time. Now this is called frequency response curve. Does not tell you when its amplitude ratio is going to reach to this quantity. For example, let's say that at omega over omega n equal to 3, then the amplitude is this value. Okay, this is the amplitude. You can extend this and find how much is the amplitude or substitute in the equation, but does not tell you when it's going to reach to this amplitude, because this shows amplitude versus frequency, and this is why it is called frequency response curve. There is time response, which means the amplitude with time. Okay, that will come from the total solution. So the particular solution alone is, and the amplitude is only related to the frequency. Okay, so for the 3 cases we discussed before, for the range of omega over omega n, we have omega over omega n less than 1. Okay, and omega over omega n equal to 1, and omega over omega n greater than 1. And let's see what happened at those ranges. So for omega over omega n less than 1, of course, if not cosine omega t, and this is the plot of a cosine wave, x is going to be, the capital X is going to be positive. So it means that, and the phase of course is 0. So it means that x, p, and f are in phase. That is positive. When f is positive, x is positive. This is called in phase. And if f is negative, x is negative as well. Okay, this is for z equal to 0. This is called in phase. So the mass it follows the force. So if the force is positive, it means it is going, let's say, downward. The mass will move with the force downward. And if the force is pushing upward, its direction is upward, the mass is going with the force upward. So it follows the mass, the force. The mass follows the force. Okay, so this is in phase response, and which means phi equal to 0. Okay, the case when omega over omega n greater than 1. So as you can see from the graph, from the equation, that when omega over omega n greater than 1, then we get the negative quantity for the amplitude ratio, which means this is the force is repeated here, which is F naught cosine omega t. But the response, the particular solution is going to be negative when the force is positive. So when the force is positive here, x is negative. And when the force is negative, this is positive, and so on. And this is called out of phase. And the phase, it means equal to 180 degrees. The force and the mass are moving in opposite direction. So if the force is positive, let's say it is moving down, it is pushing downward. The mass is moving upward in the opposite direction. And when the force is negative, which means this direction is upward, the mass is moving downward in the other direction. So that is the out of phase, and this occurs when omega greater than omega n for zeta equal to 0 or for c equal to 0. For zeta not equal to 0, we have seen that it will be greater than 90, that the phase is greater than 90 here. And for omega over omega n, the phase will be less than 90. So there is lag or there is lead, but that will be not 0 and 180. It depends on how much is the value of zeta. Now the response, the total response, this is the equation for the total response when omega less than omega n. Okay, so it can be used valid for all omega, but not equal to omega n. So it means it can be used for omega less than omega n and for omega greater than omega n. This equation is valid. So the total response, you can use MATLAB or Excel. If you have all the parameters, you can make a plot of this equation and use this equation to plot the response, the total response. Okay, but when the case, when omega equal to omega n, we have a ratio is 1, and we will have division by 0. The amplitude ratio will go to infinity, or x will go to infinity, which is the resonance. This is the resonance case. And the equation for the response is not valid. This equation is not valid. X equal to x0 minus f naught over k minus m omega squared cosine omega n t and so on is not valid. So what we can do, I will rewrite this equation to group similar terms together and see how we can use it to find the response of the mass when omega equal to omega n. Okay, so the above equation is written here. This is the same, but I took this factor as a common factor. F naught over k, 1 minus omega over omega n square as a common factor, which is here. Okay, you can take this as a common factor. And F naught over k minus m omega square, if you divide by k and multiply by k, you will get 1 over 1 minus omega over omega n square. Multiply by F naught over k. So when you take this as a common factor, then you will have cosine omega minus cosine omega nt multiplied by F naught over k minus m omega squared. Okay, F naught over k minus m omega squared, you multiply, you divide by k here, divide by k, this will give you F naught over k 1 minus omega over omega n squared. So you can take this as a common factor, and then the resonance is here. Okay, so this is rewriting the response equation. Which is the total solution. But in this form. So x naught cosine omega nt is there. This is x naught cosine omega nt. Okay, so this is one term. And plus x0 dot over omega n sine omega nt is the second term. Okay, so x naught cosine omega nt plus x0 dot over omega n sine omega nt. And as I told you, I will take f naught over k over 1 minus omega over omega n square as a common factor. Cosine omega t minus cosine omega nt. This is same as the previous equation. Which is valid for all omega not equal to omega n. There is no changes here. Okay, but the reason for putting this equation in this form is when you put omega over omega n, when you put omega equal to omega n, which means you will see here cosine omega n, when omega equal to omega n, minus cosine omega n, so this is 0. And this will be 1 minus 1, which will be 0. So it will be a 0 by 0. Okay, so this equation, we have to use the limits, the limiter rule, because we have a 0 divided by 0 term. Okay, limiter rule, we take the limit. So the first two terms are not function of omega, so they will be the same. The last term is going to be affected. Okay, so I'm going to write this one here. So at resonance, we have x equal to x0 cosine omega nt plus x0 dot divided by omega n sine omega nt plus f naught over k. We take the limit as omega goes to omega n, and the term are cosine omega t minus cosine omega nt divided by 1 minus omega over omega n squared. So now you can see This term is function of omega. So when you put omega equal to omega, you will have a 0 divided by 0. We apply L'Hopital rule, which means we take the derivative of the numerator with respect to omega and the denominator with respect to omega, and then substitute. Okay, so here when we substitute at the first time, we will have 0 divided by 0. So I'm not going to do that. Okay, so this will be the same plus if not over k, and then the limit as omega goes to omega n, and then we take the derivative with respect to omega. So this will be minus t, because we are differentiating with respect to omega. The limit is for omega goes to omega n. So the derivative will be with respect to omega. Okay, shall I do it step by step maybe? So this will be d by d omega of cosine omega t minus cosine omega nt divided by d omega of 1 minus omega over omega n squared. Okay, this is the L'Hopital rule. Okay, so this equal, this will be, those two terms will be the same, plus if not over k, and limit of when omega goes to omega n. Okay, the derivative of omega, cosine omega is minus t sine omega t. And derivative of cosine omega in t is 0, because this is not from, there is no omega here. And this is in the denominator, d by d omega of 1 is 0, and minus 2 omega over omega n squared. We are differentiating with respect to omega. So omega n squared, we'll keep it as it is. Okay, and now we'll substitute for omega equal to omega. So this becomes those two terms as they are, plus if not over k, and here we have minus and minus becomes plus, right? So this will become t sine omega n t divided by minus 2 omega n divided by omega n squared. Okay, so simplifying, we will get x0 cosine omega n t plus x0 over omega n, x0 dot over omega n sine omega n t plus if not over k, and here 1 omega will cancel with, I mean 1 omega n will cancel with 1 omega n, so this becomes if not over times omega n divided by 2k multiplied by t sine omega n t. This is the final equation. Okay, so the first two terms are the same. The last term reduces to if not omega n over 2k t sine omega n t. You see, this is the same, right? Yeah, so it is x0 cosine omega n t plus x0 that over omega n sine omega n t plus if not omega n over 2k times t sine omega n t. The plot of each term, and those are added. So the plot of cosine omega n t is amplitude is the same, right? Which is equal to x0. Amplitude of the second term is a sine wave. Amplitude is the same. equal to x0 dot over omega n. The amplitude of the third term, the coefficient contains t, is a equation of a straight line. So it is going to be increasing with amplitude is increasing as f naught over 2k omega n t. That is the amplitude. It's increasing as a line, as a straight line. Which means this is open. So this is when you put the three together, let's say we have zero initial condition for x as 0 equal to x0 dot equal to 0. The first two terms will cancel out. You have only the third term. And this is the response with time. This is the time response. Amplitude is increasing linearly. And there is no bound. This is diverging. Which means there is no limit. So it is increasing without bound, and it will reach to infinity. That is what the frequency response is suggesting. If we go back to the frequency response curve, at omega equal to omega n, the amplitude ratio or the amplitude is going to infinity. Okay, but it does not tell you when. And of course, there is no spring can handle this magnitude of displacement. It's going to break at some point. Okay, so you can make a plot for an interval of time. You will see that the amplitude is increasing linearly, but when the spring is going to break, it's something else. We have to know the geometry and the material of the spring. Okay, so this is what happened at resonance, which is, this is dangerous case. This is to be avoided, especially if you have no damper. Okay, most machines are not supported by viscous dampers because their working condition is omega over omega n is very much greater than 1. So it will be in this range, that is at 4 or at 10, that the amplitude ratio is very small. And the machines will be running smoothly at high speeds and at high frequencies. The problem in machines is usually the imbalance, and the imbalance is related to the rotating speed. So if you have machines running at high speed, it means it will have an amplitude is going to be very small. But if it is at resonance, it will have a problem. So if you are calculating the response at different times, but you have to know what is omega. If omega is not equal to omega n, then you can use this equation, number 1. If omega equal to omega n, then you should use equation number 2 to calculate the response at different times. This is one of the phenomena. That is the resonance, which is a problem that occurs in vibration, and that to be avoided. Another phenomena is called beat phenomena, in which we have the omega is not equal to omega n, but very close to omega n. So this beating phenomena occurring at omega is almost equal to omega n. So still you can use the same equation, number 1, because omega is not equal to omega n. Even if you have a small fraction, this will not be division by 0, so it will work. For 0 initial conditions, equation 1 is written in this way. Okay, this is exactly same as equation number 1 above. Okay, but what we did here is f naught over k over 1 minus omega over omega n square is simplified different way. So we have f naught over k over 1 minus omega over omega n all squared. Okay, we can multiply by omega n squared minus omega square all divided by omega n squared. So it is f naught omega n squared over k. And omega n square is k over n. So this will be f naught over n over omega n square minus omega squared, which is this one. F naught over m over omega n square minus omega square cosine omega t minus cosine omega n t, which is those two terms in the bracket. It's the same. Now, the reason putting this in this form, I will take just 1 or 2 minutes. The reason of putting this response in this form, because omega is very close to omega. So you can plot, if you are using Excel or MATLAB, you can plot the equation number 1 for omega very close to omega n, and you will see the response. But this is mathematically is proven what will happen when omega is very close to omega n. We're using trigonometric identities. Cosine omega t minus cosine omega n t is 2 sine omega plus omega n over 2 times t multiplied by sine omega n minus omega over 2 times t. Okay, you can prove this by expanding. And if you expand this, you will see that you are getting the same as. So this is the whole thing here is equal to 2 sine omega plus omega n over 2 times t sine omega n minus omega over 2 times t. Okay, for omega is very close to omega n, you can give some numbers. Let's say omega n minus omega is equal to 2 times epsilon. Epsilon is a small number. Okay, and omega plus omega n is going to be 2 omega. This is approximation, as you can see. Because omega is very close to omega n, so you can say that omega plus omega n is 2 omega. And omega n square minus omega square becomes, this can be factorized, right? Omega n minus omega multiplied by omega plus omega n. Omega minus omega n minus omega is 2 epsilon. Omega plus omega n is 2 omega. So this becomes 4 epsilon omega. Okay, so the response becomes sine x equal to f naught over m over 2 epsilon omega. There is 4 here, right? And there is 2 here. So 2 and 4, then you get divided by 2. Sine epsilon, sine omega plus omega n over 2 is omega. So this becomes sine omega t. And sine omega n minus omega over 2 times t becomes sine epsilon t. So this becomes f naught over m, 2 divided by 2 epsilon omega sine epsilon t sine omega t. The frequency of excitation is omega, and the response, the mass is going to oscillate with omega. So its amplitude, this is the amplitude, is changing as a sine wave, not as a straight line. In the resonance, it was changing as a straight line. Here it is changing as a sine wave, as shown here. This is a typical response. So amplitude is building up to maximum. This is maximum. Then dies out. It becomes 0. And then start building up to maximum. And then dies out to 0 and keep cycling this way. The frequency of oscillation is omega, and the period of oscillation is tau equal to 2 pi over omega. But the frequency of beating, this is beating, there is beating here, as you can see. Amplitude goes to 0 and then build up again, then goes to 0, is 2 pi over epsilon. 2 pi over epsilon. This is the frequency of, this is the period of beating. Okay, tau b. Okay, so we will do the example next time and then move to lecture 5. Who's coming today for the makeup? Riyad, are you coming?
Yes, Doctor. I will.
Okay, but as I told you, you are repeating, right? You did the test one.
Yes, Doctor, I did.
Okay. Okay, so you will have the chance to repeat, but make sure that you score full mark in the questions. So
Okay, Doctor.
the way I will mark it is different than other who were absent. يلا بالتوفيق إن شاء الله.
السلام.
مع السلامة.